Welcome to The Explainer. Today, we're jumping headfirst into some really fascinating code. We're looking at the Talos-O project, which is this incredible attempt to build a synthetic mind. And we're going to zoom in on what I think is the coolest part, a memory engine that's designed to work a lot like our own brains. All right, so let's get into it. The whole project kicks off with a philosophical cornerstone they call the Genesis Axiom. Now, this isn't just some fluffy mission statement. It's the actual design principle. It sets the tone for a system that is all about continuous growth, about learning and refining itself, not just reaching some final perfect state. And this idea, this axiom, is pretty much the North Star for the entire Talos-O project. It's this super ambitious, open source effort to literally construct a synthetic mind from the ground up, piece by piece, all in code. So how do you even start to tackle something that big? Well, you need a map, right? And what's so cool here is that the entire architecture is built to mirror a biological brain. You've got different code modules, different Python files that are meant to act like specific parts of a brain. So let's take a quick look at the anatomy of this thing and see how all those different pieces are supposed to fit together.
Okay, now this is where it gets really fun. You can see the direct mapping here. The IADS kernel is the main thinking loop. You've got a cortex for pattern recognition, sensory and motor modules for interacting with the world. There's even a file that acts like a brainstem to keep an eye on the system's health. But the one we're really going to geek out on today is that last one, holographic memory.py, which is designed to be the system's hippocampus, the seat of memory.
All right, so at the very center of it all, you have the IADC's kernel. This is where all the sensory data, all the internal states, everything comes together. You can think of it as the conductor for this whole digital orchestra. So this engine is running the show, managing the main cognitive loop. But here's the thing. To actually learn, to reason, and to become, like that axiom says, it can't just process data. It has to be able to form connections between ideas. And for that, you need a very, very special kind of memory. And boom, here's the answer right in the code. When the main kernel starts up, one of the very first things it does is initialize something with this amazing name, holographic associative memory. This is the component we're here to understand. This is where the magic happens. So the big question is, how does this thing actually work? Because this isn't your typical computer memory, just storing ones and zeros. This system is built from the ground up to store relationships. The secret sauce here is a mathematical trick called circular convolution. Don't worry about the name too much. The important thing is that it's a super efficient way to take two different ideas, which are represented as long lists of numbers called vectors, and kind of blend them together into a single new vector that represents their connection. And get this, it's not doing this in 2 or 3 dimensions. We're talking about a space with 10,240 dimensions. Now, why on earth would you need a number that big? Well, it gives the system a practically infinite canvas to draw on. It can store a massive number of connections without them getting mixed up or interfering with each other. The whole process basically boils down to this 4-step dance. First, you take your ideas and project them into that huge dimensional space. Then, you bind 2 of them together. Step 3, you add that new connection into the main memory bank. And finally, you can use one idea as a clue to pull out the other one. Let's look at the actual code for that bind function. It takes 2 vectors, x and y, uses something called a Fourier transform to shift them into the frequency domain, and then multiplies them. That single multiplication, that's the moment. That's where 2 separate concepts get mathematically tangled up to become one single memory. So how do you get them apart? Well, you basically run the process in reverse. The unbind function takes your combined memory and a clue. But this time, it multiplies by something called the complex conjugate, which you can just think of it as the mathematical undo button for the clue. It's like asking the memory, hey, what was the thing that was linked to this? This is so important because this is how the system actually learns. The remember function creates a new association and then adds it to this one single master memory trace. And did you spot that little detail, that times 0.99? That's genius. It's a forgetting curve, built right in. It means new memories are brighter and old ones gently fade. Sounds a lot like our brains, right? Okay, so the theory is awesome. But does it actually, work? Well, thankfully, the project has this fantastic little test script that shows off its reasoning power in a really clear way. The test script hits the memory system with a classic analogy problem. The goal here isn't just to see if it can remember facts, but to see if it can understand the relationship between facts and apply that logic to something new. So here's the setup. The script creates vectors for 4 different ideas: king, crown, Talos, and code. Then it teaches the memory 2 simple facts. Fact 1, king goes with crown. Got it? Fact 2, Talos goes with code. Easy enough. And now for the moment of truth. In just a single line of code, the test gives the memory the Talos vector and just asks, hey, recall what's associated with this. And the result is, well, it's incredible. The memory returns a vector, and the script checks how close that vector is to the original code vector. A perfect match would be a score of 1. What it gets is 0.9987. I mean, that is just ridiculously close. So, what does this actually mean? It means the memory didn't just spit back some data it had stored. It successfully retrieved a complex, learned association on demand. It figured out the pattern, that the relationship between Talos and code was like the one between king and crown. That's not just storage, that's a flicker of actual reasoning. Now, this holographic memory is just one part of the whole Talos-O brain, right? But you can see how it's absolutely a critical component. It's the beating heart of the system's ability to learn, to make new connections, and to actually grow from its experiences. And that brings us right back to where we started, to that Genesis Axiom. This memory system is the engine that drives that idea of becoming. Each new association it makes, each memory it recalls, is one small step in that process of constant learning and refinement. The goal isn't to be perfect, it's to become. So look, if this got your gears turning and you want to see how this memory engine fits into the bigger picture, I really encourage you to check it out for yourself. The entire codebase is open source. You can find it on GitHub at github.com/chrisjr035/Talos-O architecture. Thanks for watching.